Objective for 7-1 was model exponential growth and decay. So technically, we haven't even gotten to the objective yet because we haven't done the word problem. And that's what they mean by model. But we're getting there. We're getting really close. What we did spend quite a bit of time on yesterday was figuring out the percentage of growth or decay. That's because that definitely is an MCA ACT thing, you know. They want you to be able to look at 0.34 and say, oh, that's going to be decay. $1 minus 34 cents, that'd be 66 cents. So it's going to be 66% decay, and just be able to do that and move on to the next ACT problem or next MCA problem. But what we have to do, like I said, is get to the word problems, because that's truly what our objective was about. And it says, you invested $1,000 in a savings account at the end of 6th grade. Good for you. Wonder how you got that $1,000, maybe birthdays and that kind of stuff. The account pays 5% annual interest. How much money will be in the account after 6 years? Well, we're still going to use this wonderful little formula that we have. Y equals A times 1 plus R to the T, because it is a savings account. You are going to make money. We need the plus. But what we have to do is figure out where everything's going to go. So first things first, A is initial amount. So how much did you put in that bank account? 1,000 smackers. Okay. And we got the 1 in there because, of course, you're going to get the original money back, the original 100%, but then you also want more money. What's the more money they're giving you? 0.05. And then we'll just put a little T up here for time. So it said how much money will be in the account after 6 years. Well, there's the T. So Y equals 1,000 times 1.05 to the 6. So 6th grade, you put some money in. You give it another 6 years, starting to look at college, how much do you have? 1,000 times 1.05 to the 6th power. You're going to need more money for college. Don't want to scare you, but I got a senior this year. We're looking at the cost of college. Room and board and tuition at one of the cheaper schools in Minnesota, $24,000 a year. That's at Morris. U of M is higher. Other places are higher. Calculators are going to be so, you know, it's one of those things where you have to figure out, okay, what am I going to do? I'm going to work my way through college. Am I going to take out some loans? You know, because you should, if you have a college education, you should be able to make some decent money when you get out and then start to pay back those student loans. But it ain't cheap. This $1,340.10 is not gonna do it. You know, that's your meal plan for one semester right there. Just how it works. So down here it says we have another example, an extra example, and this is about populations. 3 neighboring towns, Cedarville, Petersland, and McGee City. And it says growth or decay rates are listed below and find the populations after 10 years. And this is because when we made these notes, it was me, Mrs. Peterson, and Mrs. McDonald, who's now working at Zero. So they named the cities after ourselves. And I like my city. It's growing. Things are going well. Petersland, not so much so, you know. That's happening in cities like Detroit, where they had to close a bunch of the factories that used to make automobiles, so they're losing a lot of their population. But what we want to do is figure out how do we write this stuff. And it's going to depend on whether or not it's growing or if it is decaying. Which formula we're going to use. We just have those 2 little formulas to choose from. So for Cedarville, I see its growth. That means the plus formula. So 47,162 is what it's at right now. Gonna grow 2%. So I kind of do this math in my head. 2% is 0.02, 1 plus 0.02, that'll be 1.02, and they want to know 10 years from now. I'm just going to write the equations and then we'll punch them all in at the same time. But Petersland, uh-oh. That one's decay. starting at 39,650. But I'll have to do 1 minus 3.1. So I think, okay, well, $1 minus 3 cents would be 97 cents. But then I have to take away that little 1/10 there. So that would be 96.9. Or, I grab a calculator. Say, okay, calculator, what is 1 minus 0.031? There it is, 0.969. Again, you're supposed to find this after 10 years. McD City. Need to know which formula, so I look at, oh, it's growth. That's going to be back here to 1 plus R. So we're starting with 58,975. But 1 plus 2.35% will be 0.0235. So 1.0235 to the 10th power. All right, so in the red, I have Cedarville. In the green, I have Petersland. Uh-oh, forgot an R. And in the blue, McD City. 47,162 times 1.02 to the 10th. And notice it's not a fraction, so oops, I missed 1. I don't have to put this part in parentheses unless you want to. I mean, sometimes it's just nice to get used to the parentheses. So that's up to, and this is people, so we're not going to say we have 0.21 of a people. That doesn't make any sense. So we're going to say that that's about 57,490 people. Growing. Not huge, but it's growing. Petersland, 39,650 times 0.969 to the 10th. And they are down to 28,900 and about 39 people. McD City, 58,975. Well, that started off a little higher, and their growth is a little higher. Times 1.0235 to the 10th. So higher population in the end. 74,390, about 5 people. So we're still just using those 2 basic formulas. But we have to keep track of where does it start, and then is it growth or decay, and use the right formula. And make sure we have those 2 decimal places in there. So down here, interesting question. It says, when will the population of Cedarville reach 65,000? Use a graph or a table. So here's what we want to know. When is this going to equal 65,000? Well, 65,000 would go in for Y. And we'd have 47,162 times 1.02, but we're going to change that to X because that's what we don't know. We don't know how many years it's going to take. Oh my goodness. I know I don't write well when I'm writing below myself, but that was really awful. 47,162 times 1.02 to X. Now, if we tried to solve this by hand, we divide both sides by 47,162, but then we'd be stuck. And that's because we haven't learned logarithms yet. So what we do with this is we use good old blinkers, little blinky. We say, okay, if all else fails, I'll put this in as y sub 1, I'll put this in y sub 2, I'll mess with my window, and I'm going to make this work, doggone it. So y equals, we've got 65,000, and then I need my 47,162, and I will use parentheses here because I just want it to look really nice. 1.02 to the x. Wouldn't have to, but just want it to look nice. And now I know I've got to mess with my window because x is number of years, and you're not going to have a negative amount of years, so I've got to start at 0 there. And at 10 years, we certainly did not have 65,000. It was getting there, but we didn't have 65,000. So let's make it 25 just to make sure we could see that's 65,000. Speaking of seeing that 65,000, if we don't change our y's to something higher than 65,000, we're going to get nothing. So maybe 70,000. That should do it. Yeah. Hopefully, it'll be within those next 25 years. If not, if we don't see the intersection, we can always make it bigger, but it's a great place to start. Everybody set? Use some time. What's up, Trent? Oh, that's because it had your apps on that shade and stuff. So just skip that. We don't really care about that part, but it's the X-min and the X-max that we need. Yeah, if we were using those inequalities, and that was probably even first semester, the inequalities app gives you something called shade residual. We don't need that, so you can just kind of hit past it. Don't clear it. The calculator hates that when there's no number there. Just kind of skip it with your arrows. You ready? Alrighty, graph. There's 65,000. Come on, come on. You can do it. You can cross it. Yes! Because now Blinky can find it. If we can see it cross, Blinky can find it. Second, trace. Which one tells us where they cross? 5. Intersection. You either go down there or just punch a 5. And then Blinky needs us to hit enter 3 times. 1, 2, 3. Blinky says it's going to take a little over 16 years for that to happen. It will take a little over 16 years. Now, that, remember from product stats, is called extrapolation. Extrapolation means we don't really have data for that time period because nobody can know what's going to happen in 25 years. Maybe Cedarville has a large cereal plant, and 10 years from now there's going to be a huge scandal because they find something in the cereal plant that shouldn't be there, and the plant closes. Well, then it could be in decay, just like Detroit. So this is just a prediction. We're saying, hey, if everything stays the same, yes, it should take a little over 16 years for these to be there. So I'm going to tell you this story. If you don't want to be completely grossed out of sugar for the rest of your life, then don't listen. Anything up to the extreme heats that they have to heat the cane sugar up to, nothing will survive. There's no bacteria, there's no nothing, so yuck. Anyway, don't ever think about that when you're having sugar. You won't eat sugar ever. Iberian links. Exponential functions are often discrete. Boy, there's a word we haven't talked about in a long time. Discrete means countable. You know how we were just talking about the population and it wouldn't make sense to say, I have 47,852.85 people. You don't do that with people. So when they're countable objects, you kind of just, you round is what you do. You're not necessarily going to put it in halves, fourths, or any decimal pieces. So to model a discrete situation using an exponential function of the form y equals a times b to the x, we have to find the growth or the decay factor. And it's been a long time since I taught exponential, so I know you guys don't know the song. But the song that I made up for my exponential algebra students was slope, slope, find the slope, average rate of change. And that's because average rate of change is slope. That's what it is. So when you read a problem on the MCAs or on the ACTs, and you're going, oh my gosh, they're asking me average rate of change. I don't know what that is. Slope, slope, find the slope, average rate of change. y2 minus y1 over x2 minus x1. It's just slope. That's all it is. It's just slope. Now, it's a little different for the bottom here because you'll see, hey, they're using y again. And that's because for average rate of change, what you want to do is compare it to the original. What did you start with? So we need to find the growth or decay factor b. If you know the y values for 2 consecutive x values, you can find that with this little button right here. So all we're really doing is slope. We're finding the change in the y's and dividing it by what we had originally. And then notice this is our little growth factor, b1 plus r. So it's not a new formula, it's just that we have to do a little more work. So Endangered species, that means close to extinction, very close to an extinction level. The table shows the world population of the Iberian lynx in 2003 and 2004. And I love animals, so every year I check on them to make sure things are going better than they were back then. Bless you. So the Iberian lynx, Spain and Portugal. And Spain and Portugal are packed full of people. So there's really nowhere for the Iberian lynx to go anymore. So it says, we want to figure out if this trend continues, which was bad news for the lynx, because look at this, 150. That's in the world. There were 150 of them. And then in 2004, 30 of them had died. So now they're down to 120. So very bad trend for the Iberian lynx. If this trend continues and the population is decreasing, and it is exponentially, how many Iberian lynx will there be in 2014? So what we want to do is use our little formula, a times 1 plus r to the x, and figure out what's going on. So the first thing we'll do is figure out what's that rate of change. What happened here? Well, what happened was it was 150 and it went down to 120. So 120 minus 150 over what it originally was, which was 150. So that's going to give us our little fraction value for r here. So let's see what we get. 120 minus 150 is negative 30. And if we divide that by 150, 20%. It went down by 20% that year. So again, all we do is subtract the two y values, divide by what it was originally for y. Now it says use r in that 1 plus r formula. Well, technically I'd say we don't really need the 1 plus r formula. We could just use this as 1 minus r. But we didn't know that until we did the math. So that's why they put, let's just use the 1 plus r up here. So it'll be a times 1 plus a negative 0.20 to the x. Well, we can do that math in there. That's like $1 minus 20 cents. That's 80 cents. So what we get out of this so far is they're losing 20%, but they are keeping 80% of the population. So now I need to think about A. And I remember A stands for what it was when everything started. What was the initial amount? Well, there were 150 of them. So that's what I'm really working with. That's the model. So we figured out what we needed for that rate of change. We used that in our formula, y equals a times 1 plus r to the x. And we used what we knew about the initial amount to get that. And what they want is for us to figure out the population in 2014. So y equals 150 times 0.80. And what I would do is go back up and think 2014 is how far away from 2003? We just do a little subtraction. 2014 minus 2003, how many years? 11 years. Let's plop an 11 in here. And let's see what they believed was going to happen if this trend continued to the Iberian lynx population. 150 times 0.80 to the 11th power. Bad news for the lynx. Very bad news for the lynx. Which makes me think, how about today? I mean, if this trend had continued, 2017. So if from 2014 was 11 years, let's tack 3 more years on there. And I'm going to hit second enter and just change the number of years. So now if we do this for 14, if this trend had continued, there would only be 7 Iberian lynx in the world. But here's the good news. Somebody took notice. There are now 404 Iberian lynx right now. And those are the ones that are not in captivity. So they did a good job and they got them back to where they needed to be. And that's what has to happen. Somebody has to notice, It's just one of those things. You've got to notice. So in our model, 5A, it says, how about 2020? I mean, if this trend continued, I told you already, this kind of broke the silence there and told you what it was. But if we used that formula, 2020. Okay, again, this formula started in 2003. So what should we put in for x? Oops, write the whole thing down. So 17, let's see, second, enter, and just change that 4 to a 7. 4 less. Bless you. And if you're wondering why on earth did this happen in the first place, there was some pesticide or herbicide that they sprayed all over Spain and Portugal that killed all the vegetation. No rabbits. The lynx eat rabbits. There's no rabbits to eat. They starved to death. So they tried to repopulate the rabbits around there, and that helped the lynx. B says, if you graph this model, would it ever cross the x-axis? Well, that's a strange question. Let's see. So, was this growth or decay? Definitely decay. So it was going to look like this. Their question is, are we ever going to drop below this x-axis in this problem? Why not? Can't have a -6 lengths. Can't happen. 0 is going to be the lowest you're ever going to go. And we can't have a negative amount of years, but in this one it wouldn't be the years, it would be negative, it would be the lengths. Can't have a negative amount of lengths. So there's another example of, kind of thinking through that discrete piece. You can't round, you can't have half a lengths, it isn't going to happen. And we can't go below 0, we just can't. So I know they're word problems, but I want to see your 4, 3, 2, 1, 0 and how you're feeling about figuring out what A needs to be, doing that average rate of change. That's good. Not bad numbers at all, everybody. Good job. All right. Then let me get you this. There was a big thing in the paper, in Minnesota and Iowa, at, what was about the beginning of the school year. Shoot, now I forgot the name of the thing. Fishers. You ever seen a fisher? Like at the DNR station that kind of looks like a ferret, kind of. It's called a fisher. In Iowa, there had been no fishers for about 100 years. And somebody caught a picture on their little motion sensor hunting cam of a fisher in Iowa. So we had so many in Minnesota that they spread out and headed down to Iowa. So that's good news for the fishers. Now we can just get the moose stores contact. The moose in Minnesota not doing so good.